Hello everyone, welcome to this video. In this video, we'll be studying about this result which states that a normal subgroup is always a kernel, right? How is this possible? Remember, we have studied about this result which states that the kernel of every homomorphism of a group, suppose we define some homomorphism phi from group G to G bar, then whatever is the kernel phi of this homomorphism, right, that is a normal subgroup of this group G that we have already studied. Now we wanted to look at the converse. Now with the same condition, can we say that the normal subgroup of G is a kernel of some mapping phi? Actually, from the group G, you can create so many mappings from it, right? So for each individual mapping, we would have different kernels, right? Kernel I or kernel 1, kernel phi 1, kernel phi 2, and so on, right? So you can construct different kernels. Now, and moreover, this group G can have very many normal subgroups within it. So for each normal subgroup here, they are saying, can we have a kernel for some specific homomorphism? The answer is yes, this thing is true. And we also have a theorem for it. It states that every normal subgroup of group G is the kernel of the homomorphism of G. And in particular, with the notations, you can define it like this. You can define some mapping from the element G to the element G capital N, where what is capital N? It is the normal subgroup, right? So we say this normal subgroup here is the kernel of this mapping, and this mapping has been taken from G, the group, to its factor group, right? So this is there. So using this outline here, we can prove this result. So if we first of all define the mapping, let's call it by the name gamma. This mapping gamma takes the element G to the element to the group which is the factor group of the group G constructed by this normal subgroup N, right? And we define it like this, that when you take some element small g from the group capital G and apply gamma onto it, you obtain here. So that means you reach at some coset of this factor group, correct? Factor group contain cosets that you already know. So this mapping has a particular name. The name is natural homomorphism from the group G to its factor group, correct? Now we first of all show that it is homomorphism. So for that, we take two elements X and Y from G. For those two elements X and Y, we apply gamma onto it. So by the definition of gamma, it would be equal to xy of n. Now it is a coset. By the properties of coset, you can write it like this, x n y n, right? There is no issue. And what is x n? By the definition, it is equal to gamma of x, and y n by the definition is gamma of y. Hence you are able to prove that gamma of xy is equal to gamma of x into gamma of y. Hence we show that this mapping gamma is a homomorphism. This is one part, correct? Now because we have proved gamma to be a homomorphism, if we take N to be the normal subgroup here, we wanted to show it is the kernel of this mapping gamma, right? So we consider N to be the normal subgroup of G. We wanted to prove that this normal subgroup is basically the kernel of gamma. So we will prove N is equal to kernel gamma. So we first of all show N is present within kernel gamma, and then kernel gamma is present within N, correct? So here we take some element from kernel phi, taking some element G from here. By the definition of kernel phi, if you apply the mapping gamma onto G, you would obtain the identity element, right? Identity element of what? Of G by N. And what is the identity of this factor group? It is just the normal subgroup N. So it is equal to N. And by definition, what is gamma of G? By definition, we have defined this gamma of G to be G of N. So G of N is equal to N here, right? And by the properties of this coset, You also know that if you have AH is equal to H, then that implies A belongs to H. Similarly, if you have Gn is equal to N, then that surely implies G is contained in H. And this is a two-way process. So that means if you start from G, which is present in the kernel, and you reach at G present in N, so that means kernel of gamma is contained in N. This is one way. Another way, you start from here, because G is present in N, which is a normal subgroup, so you can write it like this. You can write Gn is equal to N. And what is Gn? By the definition, it is gamma of G. And if gamma of G is equal to N, which is the identity of this factor group, hence you can write G is present in the kernel. Hence, from here we see that N is present in the kernel gamma. From this relation 1 and 2, you can clearly say that N is equal to kernel gamma. Hence, every normal subgroup gives rise to some kernel of the homomorphism defined from that particular group. So this is the result. So I hope you understood this result well. Well, that is it for this video. Thank you for watching.